Now, I've already told you that we do have a test coming up. And this test, and really this unit for the most part, is almost all vocabulary. Some of it you've already seen, some of it you haven't. So definitely pay lots of attention to the vocabulary. We are going to start with a quick little video. It's going to have a lot of the vocabulary for this unit in it, so pay attention. After the video, we do have an amazing set of notes. I know that you're very excited. It's been a long time since we've done notes. So, first, yay video, followed by yay notes.
Imagine an earth without water, life without water. We find it everywhere, in the atmosphere and below our feet. 3/4 of the Earth's surface is covered by this essential liquid. It's a difficult thing to imagine life without water, because our own survival depends on it. In fact, water is vital to the existence of all forms of life on Earth. Water, or H2O, is an unusual compound with amazing properties. These unique properties are what make it so important to life. First of all, water happens to be the only substance on Earth that can be found naturally in all 3 states, as a solid, a liquid, and a gas. It is rare in that it actually expands as a solid, which is why ice can float. Pure water is essentially colorless, odorless, and tasteless. Water has a neutral pH, which means it is neither acidic nor basic. Water has been called a universal solvent because it can dissolve many substances. Wherever water goes, either through the atmosphere, the earth, or through our bodies, it takes along valuable chemicals, minerals, and nutrients. This is one reason why water accounts for about 70% of the weight of a cell, which is the building block of life. Water has high specific heat, which means it absorbs a lot of heat before it changes temperature. This is why water makes a great coolant. This is also why oceans, lakes, and water vapor in the atmosphere help to regulate the Earth's temperature. Water molecules are sticky. They attract to each other, which is why water tends to float together, fall as raindrops, and bead up on the surface of a leaf. This property is the result of cohesion. To understand cohesion, let's imagine we're recreating a water molecule. A water molecule is made up of 2 hydrogen atoms and 1 oxygen atom. Because of the molecule's arrangement, and the electronegativity difference between the hydrogen atoms and the oxygen atom, the molecule becomes polar. The oxygen atom has a negative charge, while the hydrogen atoms have a positive charge. Since we all know opposites attract, the oxygen atom will stick to a nearby hydrogen atom. The result is a strong bond. Surface tension is a result of cohesion and is the measure of how difficult it is to break the surface of a liquid. We can observe the high surface tension of water by watching this mosquito step onto its surface, or this insect as it struggles to free itself from a droplet. Surface tension is also what causes a water droplet to take a spherical shape. Water is the most cohesive of all non-metallic liquids. Adhesion is similar to cohesion, but refers to 2 different surfaces or molecules with an attraction to one another. This is why the droplet sticks to this leaf. Along with cohesion, adhesion is responsible for a phenomenon called capillary action. Capillary action is the force that pulls water upward against gravity through a narrow tube. This is an essential property for plants, which rely on capillary action to pull water from their roots up to their leaves. So So it's pretty obvious that water is important stuff. Humans rely on it for personal consumption, as well as things like industry, energy production, and agriculture. But we sometimes have a tendency to use more than we need and pollute what's left. We need to make sure we keep it pure and plentiful.
So continue on yay notes. Now, first thing, it did talk about this in the set of questions you just had. It also talked about in the video that all living things are dependent on water. It said cells are 70% water. All living things have cells, so water is essential. And water is very unique. It is a very unique liquid. It has properties that are different than almost everything else. The most important of these properties is hydrogen bonding. And we're going to go into what hydrogen bonding actually is in just a minute. So, first thing I asked you to do in that little assignment was to draw a water molecule. And some of you did an excellent job of that. Others had a few issues. First thing that you need to notice, water is a bent molecule, meaning kind of forms a V shape. The hydrogens don't ever touch each other, they only touch the oxygen. So it's going to form this bent V shape like it shows up there. It does have two hydrogens, one oxygen, just like that. The oxygen side is going to be negative. The hydrogens are going to be positive. And when I say that, I mean a slight negative charge and a slight positive charge. Remember when we bond atoms? It's actually the valence electrons that are doing the bonding. So we have our oxygen right there, covalently bonded to two hydrogens, just like this. And it's that bent shape that we were talking about. Now we said that they are sharing electrons, sharing valence electrons. Well, the oxygen's a little bit greedy. It's going to take those electrons, it's going to pull them in closer. So when we're actually looking at this, we could actually say those electrons that are shared, they're right over there, really close to the oxygen. They're further away from the hydrogen. So since it is close to the oxygen, we're going to say that the oxygen has a slightly negative charge and the hydrogens have a slightly positive charge. So the oxygen is slightly negative, the hydrogens are slightly positive, and that's all because of where the electrons are actually located, closer to the oxygen molecule. They're slightly negative. Do y'all remember what charge electrons have? Negative charge. That's why I'm basing all this on negative. Since it has the electrons closer, it has more negatives closer to it. That's why the oxygen is slightly negative. Overall, it's a neutral atom. A neutral compound, because the slightly positive, slightly negative cancels each other out. But each side of it does have a charge. And that's called polar. It has poles, just like a magnet has poles. So it has a positive side and a negative side. Now, hydrogen bonds happen between two different molecules. So a hydrogen bond does not happen inside one water molecule. It happens between two different ones. It's when the positive side of one water molecule is attracted to the negative side of another. So the hydrogen on one water molecule will be attracted to the oxygen on another. Now, a hydrogen bond is not as strong as the covalent bond. You do have a covalent bond that's connecting the oxygen and hydrogen on the specific water molecule. So right here is a covalent bond. That's a pretty strong bond. This thing right here is not as strong. That's the hydrogen bond. But it does provide water with all of its unique characteristics. So we have the negative end attracted to the positive end of another. This is a hydrogen bond. Now, properties of water. This is where a lot of that vocabulary that I was telling you about is going to come in. So the actual properties that water has. First thing, boiling point, freezing point. Water has very specific boiling and freezing points, and you must memorize them. Now, these boiling and freezing points that I'm going to give you are at sea level. So at sea level. So when our air pressure is normal at sea level, pure water will boil at 100 Celsius and it will freeze at 0 Celsius. If you go up into the mountains, that changes because you're not at sea level anymore. The boiling point actually goes down. But when I'm giving you the standard boiling points, that's at standard pressure at sea level. Now here's a list of all the different properties that we are going to be talking about. Take a second, write these down. You have space on the side of your paper. Go ahead and list these out. Water does have a very high specific heat. We're going to go into more detail in just a minute on what that means. It has high heat of vaporization. It is less dense when it is a solid. It's a solvent, meaning it will dissolve things. It will organize things it cannot dissolve. It will form an ion. We're going to learn what ions are. It has cohesion. It has adhesion. And it has hydrogen bonds. All right. So the first thing we had on that list was specific heat. Now this is a very important thing of water. It is one of the reasons our weather is the way it is. We learned about this when we talked about the oceans. Most of the earth is covered in water. And if you live near an ocean, your temperatures stay about the same year-round. Water will moderate the temperatures. It will absorb all that energy from the sun without changing temperature much. Then at night, it will release that energy back to keep the temperature about the same year-round. So very important for our weather that water has a high specific heat. And it can absorb an enormous amount of energy. Other things that we have do not have high specific heats. Like this metal chair. Do you think it has a very high specific heat? If I put a flame to this metal chair, would it heat up fast or would it heat up really slow? It would heat up very fast. If I put that same amount of heat to a cup of water, would it heat up fast or slow? So after just a little bit, that metal chair right there, you wouldn't want to touch it anymore because it would be too hot. But the water, if it had that same amount of heat, would you hold it? Sure, it wouldn't be very hot. Because water has a high specific heat, it can absorb just an enormous amount of energy. That chair right there has a very low specific heat. That's why we use metal for pots and pans. Because it heats up so quick. We don't want to spend all of our energy just heating the pot. We want that energy to be transferred to whatever we're trying to cook. Next thing, heat of vaporization. Now it just makes sense. If water takes a lot of heat to heat up, or a lot of energy to heat it up, it's going to also take a lot of energy to make it change from a liquid to a gas. So not only does it have a lot of energy needed to heat it up, it's going to take a lot more energy to go from that last bit to go from liquid to gas. The reason is, water has these hydrogen bonds. So you can heat up water all day. Heat it up, the hydrogen bonds are still there. But before it can become a gas, you have to add more energy to break those hydrogen bonds, and then the water molecules can be free to float around. So the high heat of vaporization is due to the fact that you have a hydrogen bond there. You have to add even more energy than just the normal to make that hydrogen bond break and to release the gas as it comes out. Next, once we have that water vapor, that gas released, it's going to hold in the heat. So we have the sun heating up the air. Now the water in the air is going to keep a lot of that heat there even at night. That's called humidity in the air. If you really want to experience humidity, just go to Houston in August. Everywhere you walk, you feel like you're walking through a swamp. It's kind of disgusting. If you do not want to experience this, you can go to Phoenix, Arizona in the middle of August. It's a nice, brisk 115 degrees outside, but the humidity is almost nothing. So it actually feels hotter in Houston because of all that swampy heat than it does in Phoenix without the humidity. Okay, next thing, very important. Water is less dense as a solid. Now, this doesn't happen often. Most things, if they become a solid, they get more tightly packed in, and that means they are higher in density. But water is actually lower in density. Very important for all of you future aspiring competitive ice fishermen. If ice did not float on water, there would be no ice fishing. There would be no life at all in our water, because every winter, as soon as it got cold, if the ice sank to the bottom, lakes, oceans would completely freeze. And that would be bad. The way it is now, all the ice stays at the top, creates a nice insulating layer. Then all you have to do is go get your big drill a hole in the ice, throw in your hook and bait, and you can go ice fishing. But if it froze solid every year, that would kill all the fish, it would kill all the plants, and you have to start over every year. All right, so look at these two pictures. Which one of these is a picture of water? Which one of these is a picture of ice? Talk to your table. You get 10 seconds. Go. Okay, you are correct. The left picture is water. It's very random. Everything's kind of floating on top of another thing. The one on the right is ice. It is an exact geometric shape. It has space between the molecules. This space that is in there makes it larger. Since it is taking up more space, it has less density. Therefore, water or ice will float. All right. Next thing we need to know is solvent. Water is often called the universal solvent because it dissolves so many different things. It will dissolve anything that is polar. It will dissolve anything that is ionic. The only things it won't dissolve are non-polar things. Things like oil. There's a rule, it's called like dissolves like. Because water is polar, because it has charges, it will dissolve anything that has a charge. Anything that is like it. If it is non-polar, that means it does not have charges. That means it will not be dissolved in water. There are two types of mixtures. There are solutions and suspensions. The first thing is a solution. A solution is something that completely dissolves. You don't see the pieces anymore. We take normal salt and we put it in water and we stir it up. Do you see the normal salt anymore?
You can if there's water.
Nope, it will all dissolve. When it dissolves, the water molecules actually come in and rip apart the salt molecules. They separate and surround all the individual pieces, and it's like it vanishes. Two more words that have to do with solutions are solute and solvent. A solute is what gets dissolved. A solvent is what does the dissolving. So if we had salt and we had water, the solute would be the salt. The solvent would be the water. Next up is a picture. I thought we were going to get to suspensions, but in just a minute. You can actually see right here how all the water molecules are coming in, and you see how the water molecules surround each individual atom. So right here you can see all those water molecules surrounding the chlorine atom. And it's the positive part of the water that surrounds that chlorine, because chlorine is negative. And then right here, you can see all the water molecules, all the negative sides of the water surrounding the positive part, the sodium. And when that happens, it actually pulls each individual atom away from the solid. And as it does it, the entire thing will dissolve. Now, a suspension. Not everything will dissolve in water. Some things are suspended. It makes it look like a uniform thing, but it's not quite. An example, blood. Have you ever gone to the doctor and they take like one of those little vials of blood? What they actually do with those vials is they go put them in something called a centrifuge, something that spins around really fast. Have you ever seen the blood after it's been spun? It'll separate out into multiple layers, because blood has a lot of different things together, all suspended together. Milk is another example. A lot of different things suspended together. Another example of a suspension is muddy water. You have all these particles just suspended in the water. If you let it sit there long enough, what will happen? It'll separate out. So they're not actually dissolved in there. They're just kind of floating around. Now, water can be hydrophilic or it can be hydrophobic. Or other things can be that way to water. So, if we had something like oil, oil will not dissolve with water. They cannot mix. So it can be hydrophilic or hydrophobic, meaning water-loving or water-fearing. Hydrophobic things will actually form shapes in water. And water can also form ions. And this will lead to things like acids and bases. The OH right there, it's called a hydroxide ion. It has a negative charge. It's actually what forms bases. Now the H plus is a hydrogen ion. It's actually what forms acids. HOH together is just water. All right, looking at the time right here, we'll go ahead and stop for today. Write on your paper that this is slide 20, so we know where to pick up at tomorrow. So we did finish up at slide 20 today. We'll finish this notes tomorrow.